Hello students, welcome to EPG Pathshala. I am Dr. Shruti Thakur from University of Delhi. Today we are going to talk on module Different Astronomical Coordinate Systems under the paper Astronomy and Astrophysics. After completing this module, the students will be able to understand the simple concepts of spherical trigonometry in order to apply them to astronomy so the celestial objects can be assigned position in celestial sphere. We will learn the concepts such as the great circle, the spherical angles, the spherical triangles, poles of great circles and meridian. Under the essential requirements, we will also understand the essential requirements of an astronomical coordinate system through examples of terrestrial system which assign coordinates to a place on Earth. Understand a simple and convenient astronomical system of coordinates, the horizon coordinate system. Learn concepts such as the horizon, the great circle, zenith, the pole of horizon and horizon coordinates, altitude and azimuth. We will appreciate why horizon system is inadequate for preparing star catalogs. We will also understand the equatorial system of coordinates, appreciate the coordinates of local equatorial system, namely the hour angle which keeps changing continuously as the star moves in the sky. We will also learn that both the coordinate systems of star on the universal equatorial system remains unchanged as we move in the star. Astronomy is traditionally defined as the science which studies the location and the kinematics of celestial objects such as planets, stars and galaxies. Astrophysics, as the name suggests, studies the physical processes taking place inside the celestial object. There is no real line dividing between these two subjects. The two together study every phenomena taking place in the objects beyond the atmosphere of Earth. The internal structure of stars, nucleosynthesis in stars, white dwarf, neutron stars, supernova explosions, origin of black holes, activity in galaxies, emission of neutrinos by sun, emission of gravity waves by interacting black holes, origin of universe. These are some of the phenomena in a very long list that forms the subject matter of astronomy and astrophysics. When we look at the sky in the dark night, especially when there is little dust and little light, all the celestial objects appear to lie on the surface of a sphere, the inner surface of the sphere. This imaginary sphere is called the celestial sphere. Since all the objects are lying on the sphere, therefore it becomes very important to get familiarized with the spherical geometry. So let us consider a sphere of radius r equals to 1 unit. If a plane passes through a sphere, a circle is formed on the plane. The circle that passes through the center of a sphere is called a great circle. Any other circle is a small circle. We have shown 3 great circles and a small circle. A small circle does not pass through the center of the sphere. An example of a great circle is our equator, and an example of a small circle is Tropic of Cancer or Tropic of Capricorn. A line perpendicular to the great circle passing through the center of a sphere meets the sphere at 2 points. These 2 points are called the poles of that great circle. In this picture also we have shown points P and P prime, which are the poles of the great circles. We will learn about the spherical angle. A spherical angle is found by the intersection of 2 great circles. In the picture shown here, the 2 great circles are NKS and NLS. The intersection of these 2 great circles form a spherical angle KNL. So the measure of this angle KNL is the angle KOL subtended at the center of the sphere. As we have discussed that the radius of the sphere is fixed, so it is customary to measure angles in terms of arc. Therefore, either we say the angle as KOL or we say the arc KL. Both are similar. Now let us define a spherical triangle. A spherical triangle, which is shown in the picture, NKL, is formed by the intersection of 3 great circles, which are NLS, NKS and PLQ. We have not shown the full circles NKS and NLS to avoid clutter. These three intersection of these three great circles form a spherical triangle NKL. We will learn more about the spherical triangle. In this picture, a spherical triangle is formed by the intersection of three great circles. The spherical triangle has sides denoted by small alphabets A, B, C, and the angles denoted by capital letters A, B, C. We are all familiar with the triangles in the plane. We all know that the sum of the angles of the triangle is equal to 180 degree. But this is not the case in spherical triangle. In spherical triangle, the sum of all the three angles of a spherical triangle is greater than 180 degree. All the celestial objects appear to lie on the inner surface of the sphere, which is the celestial sphere. The observer is at the center of the sphere. In the celestial sphere, we can have infinite number of great circles, but the celestial equator is the great circle whose plane is parallel to the Earth's equator. As we have north and south perpendicular to Earth's equator, similarly we also have north celestial pole and south celestial pole perpendicular to the celestial equator, and they are in the directions of north and south poles of the Earth. This celestial sphere is an important tool in astronomy. As our eye, the human eye, is not sensitive to the distance, how far or how near a star is. So we assume that all the stars are lying on the celestial sphere. This fixes the distance of the sphere. So we finally need only two coordinates to find the position of a star. We will discuss about the coordinate systems. There are two essential requirements for an astronomical coordinate system. The two requirements are: one, to find a reference great circle, and two is to find a reference point. So let us first start with the terrestrial coordinate system. In the terrestrial coordinate system, to locate a position on the surface of Earth, longitude and latitude of that place is identified. In the terrestrial system of coordinates, the great circle equator is taken as the reference great circle, and the point K, which is shown in figure, is the reference point. This point K is the intersection of the meridian through Greenwich and the equator. A half great circle through the poles N and S is called as the meridian. So NXLS is the meridian which is passing through the position X, whose coordinates we are interested in finding out. The meridian NGS has a special importance as it has been given the name of prime meridian by international agreement. This meridian passes through Greenwich in England. Now let us find out the coordinates of a place X on the surface of Earth, which is shown in this picture. So here the reference circle is the great equator and the reference point is point K. So what we do first is we draw a meridian which passes through north-south, crossing the place whose coordinates we want to find out. Now through this meridian cuts the equator at point L. So the arc LX is called as the latitude of that place, and the arc KL is called as the longitude of that place. So the longitude is measured from K, 0 to 180 degree east and 0 to 180 degree west of Greenwich. The latitude is measured from 0 to 90 degree north and 0 to 90 degree south, which is taken as negative. The places which are above the equator, they all lie in the northern hemisphere, and the places that lie below the equator are called as the southern hemisphere. That all the points with the same latitude lie on a circle. These circles are known as circles of constant latitude. Tropic of Cancer is a circle of constant latitude which is 23.5 degree north of equator. All the points on this circle have latitude 23.5 degree north. All the points on the circle of latitude phi, shown in figure, S has latitude phi. We have seen that there are two essential quantities in a coordinate system, and these two quantities are the fundamental great circle and a reference point. This case we have studied in the terrestrial coordinate system, where the fundamental great circle is the equator, and the reference point is the intersection of Greenwich and the equator. Same thing happens in astronomical coordinate system also. We need the fundamental great circle and a reference point. So for different fundamental great circles and reference point, we have different coordinate system. In this section, we will study 4 different coordinate system: the horizon coordinate system, the equatorial coordinate system, the ecliptic coordinate system, and the galactic coordinate system. First, we will study the horizon coordinate system. To study the horizon coordinate system, we must first learn to locate the horizon of an observer at latitude phi. We know the observer is always at some latitude to the earth. So the point overhead the observer is called the zenith. So since the latitude of the observer is phi, the latitude of zenith is also phi. So we draw a line through observer passing through the center of the earth, and the plane which is perpendicular to this line passing through the center is called the horizon of the observer. Objects above the horizon are visible to the observer, and objects below the horizon are not visible to the observer. These objects are said to have set. We will see 2 examples of horizon. First is the horizon of an observer which is at North Pole, which is shown in the pictures. The line through the observer passing through the center of the earth is parallel to the line joining the north and south pole of the earth. The plane perpendicular to this line is parallel to equator, which is the horizon of the observer. For an observer which is at North Pole, its horizon is parallel to the equator of earth. For an observer at equator, the line through the observer at equator and through the center of earth is in plane of the equator. The plane perpendicular to this line is the horizon of observer at the equator. The projection of equator on the celestial sphere gives us celestial equator. Similarly, the projection of horizon on the celestial sphere gives us the celestial horizon. Horizon and celestial equator projected on the celestial sphere with Earth as a center. This is shown in the picture. Both are great circles. The celestial North Pole and the celestial South Pole are the poles of celestial equator, and the zenith and nadir, which are represented as Z and Z prime, are the poles of the horizon. We will see the horizon system of coordinates. So the 2 essential quantities are again the fundamental great circle and the reference point. What are these 2 essential quantities in horizon system of coordinates? So in this coordinate system, the horizon NWSE shown in the picture is the fundamental great circle. And we are interested in finding out the position of a celestial object at X. The great circle ZN Z prime SZ, which contains the zenith nadir of the observer, is called as the observer's meridian or the local meridian, passing through NS, which are the points of intersection of horizon and the horizon and the observer's meridian. N and S indicates the geographical north and south directions. So this N is taken as the reference point or the origin. So now we have both the fundamental equator, both the fundamental great circle and the reference point. So to find out the position of X, we draw a half great circle from zenith nadir crossing through celestial object X. The arc XL is the altitude of the star. So we know that zenith and nadir, which are the poles of the horizon, they are perpendicular to the horizon. So therefore the arc ZL is 90 degree. Since LX is A, which is the altitude, therefore ZX is 90 minus A, which is also called as the zenith distance of the celestial object. The other coordinate is the arc NL, which is called as the azimuth, denoted by capital A. The altitude is measured from 0 to 90 degree above the horizon, carrying a positive sign, and 0 to 90 degree below the horizon, carrying a negative sign. The azimuth is measured from the reference point N, 0 to 180 degree west or 0 to 180 degree east. Sometimes azimuth is also measured from S westwards from 0 to 360 degrees. So the two coordinates to specify a celestial object in horizon system of coordinate system is capital A and small a, which represents the azimuth and the altitude. We will prove an important relation that the altitude of a pole star is equal to the latitude of the observer. So this one can find out using the picture shown here. So now we know that the observer is at altitude phi. So therefore the zenith point, which is just overhead the observer, is also at an angle phi to the equator. So this is what is shown in the picture also, that the arc ZR is phi. Now the poles are perpendicular to the equator. That means the arc PR is 90 degree, and we also know that ZR is phi. Therefore the arc PZ is 90 minus phi. Z is the zenith of the observer, and this is perpendicular. The line from zenith to nadir is perpendicular to the horizon. That means the arc ZN is 90 degree. Now we know that PZ is 90 minus phi. That means the arc NP is phi. Now let us see the coordinates of the pole star. So in the picture we have the equator and the horizon of an observer which is at a latitude phi. Z is zenith, P is the pole of the equator which points in the direction of pole star. And now we have found out that the arc NP equals to phi. P, which is the pole star whose coordinates we want to find out. Since P is lying on the observer's meridian, therefore its azimuth is equal to 0. And the altitude of P is the arc from the reference point N, which is NP. And we just now saw that NP equals to phi, which is the latitude of the observer. Hence, we have proved that the altitude of a pole star is equal to the latitude of the observer. We will see why this system of horizon coordinates is important. The system of azimuth and altitude is important because the small telescopes used by amateur astronomers usually prefer altitude azimuth mounting for their simplicity. In this case, we first raise the telescope from its horizontal position by the altitude of the object under observation, and then we move it around through the azimuth A till the object is within the view of telescope. We will see the drawbacks of horizon system. The first drawback of horizon system is that the horizon for different observers is different. Since the horizon is different, therefore the coordinates of a star for two different observers at different horizons will be different. This is also shown in the picture. Zenith of observer at A at latitude is given in direction ZA, and that of observer at latitude B is given in direction ZB. The latitude of observer A is phi A and the latitude of observer B is phi B, and their respective horizons are also shown. Now, since their horizons are different, so therefore the coordinates of a star will be different for two different observers. The other drawback of horizon system is for same observer, the coordinates changes with change in time. As the Earth rotates on its axis, the stars appears to move in the opposite direction. The other drawback of horizon system is for a same observer, the coordinates changes with time. This is because of the rotation of Earth on its axis. As the Earth is moving on its axis, the celestial objects appear to move in the opposite direction in a plane normal to the polar axis. These planes are inclined to the horizon of the observer. Therefore, the coordinates keep changing with time for an observer. So this means that the horizon coordinates of an object change in time as well as with the location of the observers. So these are the two drawbacks of the horizon system. So therefore, this coordinate system cannot be used for making star catalogs. Now let us look at the second coordinate system, which is the equatorial coordinate system. So now here we will find out the two essential things, which is the fundamental great circle and the reference point. In equatorial coordinate system, the fundamental great circle is the celestial equator and the reference point is point R as shown in picture. The reference point R intersection of observer's meridian ERQT and the celestial equator. So to find out the position of a celestial object at X, we first draw a half great circle from the poles. So the half great circle PXLQ is called as the hour circle of object X. It is called as hour circle because it measures the time elapsed since the object X crossed the observer's meridian. The arc LX, where L is the point of intersection of the half great circle and the equator. So this arc LX is the declination of the object X. So this is one of the coordinates of a celestial object. The other coordinate is the hour angle, which is measured from R. So the arc RL is the hour angle, is the second coordinate of celestial object X. The arc length RL measured from observer's meridian westward to the hour circle of X is the hour angle of X. Hour angle is measured in hours. So one can convert hours to angles because we know that our earth rotates 360 degrees in 24 hours. Therefore, 1 hour corresponds to 15 minutes. Equatorial coordinates system, the coordinates of a point or a celestial object X are capital H and delta, which is the hour angle and the declination. As the earth rotates on its axis, the hour angle changes continuously while the declination remains the same. So one of the coordinate is fixed while the other is continuously changing. That is why this system is called as the local equatorial system. This is one of the shortcomings of local equatorial system, which is rectified by choosing a reference point which is not fixed but is also moving at the same speed and in same direction with the object. So this we will see in the universal equatorial system. Now let us look at the universal equatorial coordinate system. So in this coordinate system, the fundamental great circle is the celestial equator and the reference point now is the vernal equinox or the first sign of Aries. So to find out the position of a celestial object X in the equatorial system, universal equatorial system, we again draw a half great circle from the poles crossing through the celestial object at X. So this half circle crosses the equator at L. So the arc LX is the declination, is one of the coordinates of that position. The other coordinate is measured from a fixed point, which is the first sign of Aries, marked in bold, and the arc from the first sign of Aries to L, which is marked as alpha, is the second coordinate. This is called as the right ascension. So the two coordinates to find out the position of a star in equatorial system is right ascension and the declination. Now let us discuss about the reference point, which is marked as first point of Aries or the vernal equinox. So we know that the earth is revolving around the sun. If we treat ourselves as, then to us the sun is appearing as if it is moving around the earth. So this apparent annual path of sun is called as the ecliptic. When the projection of ecliptic is taken on the reference point, which is the first point of Aries or the vernal equinox, we know that earth is going around the sun and it takes 1 year for earth to make one revolution around the sun. If we think that we are at rest, if we treat ourselves at rest, the sun appears as if it is going around the earth. So this is the path, this apparent path of sun when taken as projection on the celestial sphere is called as the ecliptic. So the ecliptic is also shown in the picture. So the intersection of ecliptic and equator is the point which is marked as the first sign of Aries. or the vernal equinox. So this is our reference point. Moves just the way star X does. So there is no relative motion between X and the vernal equinox. Therefore, the second coordinate measured from the first sign of Aries eastwards of X remains unchanged as X moves around the Sun. This coordinate is called as right ascension and denoted by alpha. This coordinate is measured in hours, as the vernal equinox also completes one round of sky in 24 hours. Therefore, alpha is unchanged. Since both the coordinates remains unchanged in this system as the celestial object moves around the Earth, this system is called as the universal coordinate system. This system is used for preparing the star catalogs. The plane of apparent annual motion of Sun in the sky is called the ecliptic. It is inclined to the plane of equator at an angle of 23.5 degrees. The two planes intersect at 2 points, which are represented as first sign of Aries and also called as vernal equinox. The other point is called as the autumn equinox, respectively. Around 21 June, the Sun is at a position which is in the north, which is called as the summer solstice. So this is 23.5 degrees north of equator. On that day, it rises 23.5 degrees north of east. The position opposite to summer solstice occurs at around 23 December. At this position, the Sun is at winter solstice. This is 23.5 degrees south of equator. On this day, Sun rises 23.5 degrees south of east. So the rising point of the Sun keeps oscillating between these 2 points. So if you live on the equator, the Sun rises exactly in the east for only 2 days in the whole year. These 2 days are the autumn and the vernal equinoxes. So students, let us now summarize what we have learned in this module. Astronomy and astrophysics study together kinematics of celestial objects and the physical processes taking place inside the object. Celestial sphere is the imaginary sphere on which all the celestial objects appear to lie. A great circle on the celestial sphere is the one which passes through the center of the sphere. A line through the center perpendicular to the great circle intersects the spheres at 2 points. These are the poles of the great circle. A spherical angle is formed when two great circles intersect. Since the radius of the sphere is fixed, spherical angles can be measured in terms of arc lengths. A spherical triangle is formed by the intersection of three great circles. The sum of angles of a spherical triangle exceeds 180 degrees. Since the radius of celestial sphere is taken as unity, any object on it is represented by two angle coordinates. For example, in terrestrial coordinate system is an example of an astronomical coordinate system. A half great circle joining the poles is called a meridian. By international agreement, the meridian which passes through Greenwich is called as the prime meridian. A point on the terrestrial sphere is represented by two coordinates, the longitude and the latitude. All points on Earth with the same latitude lie on a circle. Latitude ranges from 0 to 90 degree north and 0 to 90 degrees south. Longitude ranges from 0 to 180 degree east and 0 to 180 degree west from Greenwich. Depending on the choice of the great circles and the reference point, there are four systems of astronomical coordinates. The essential requirement for astronomical coordinate system are a reference great circle and a reference point. For horizon system, the reference great circle is the horizon of the observer and the reference point is the intersection of horizon and the half great circle zx z prime. The arc length along zx z prime from the horizon to x is called the altitude of x. Either the north or the south point of the horizon is used as the reference point for measuring the azimuth of x. Horizon system is very convenient system and most small telescope use alt azimuth mounting. Horizon for each observer is different. Moreover, the horizon for same observer changes as the Earth rotates on its axis. The two drawbacks of horizon systems are that the coordinates changes with the observer and with the time for the same observer. These drawbacks are sought to be rectified in the equatorial coordinate system. Equatorial coordinate system uses celestial equator as the reference great circle and the intersection with the observer's meridian with the great circle through the poles and the zenith as the reference point for measuring the hour angle of the object X. In hour angle declination system, the declination of an object is fixed while the hour angle of the objects keep on changing as the Earth rotates. This shortcoming, a coordinate changes with time, is rectified by choosing the first point of Aries as the reference point. The first point of Aries moves just like the object X, so the coordinate measured from this reference point to the hour circle of X stays fixed. This coordinate is called as the right ascension. The right ascension declination system is called the universal equatorial system. Since both the coordinates of a star in this system remains unchanged as the star moves about the sky, this system is suitable for making catalogs of stars. The annual path of Sun, which is called the ecliptic, is inclined to Earth's equator at an angle of 23.5 degrees. At summer solstice, the Sun is at 23.5 degree north, and at winter solstice, the Sun is at 23.5 degrees south. This motion of Sun is responsible for shifting point of sunrise during the year. Thank you.